to be in up state, then the second one will be measured in down state, and vice versa. So that's called entanglement. Now if you do a measurement on this particle over here, and you measure it up, this one will show down, or if you measure it to be down, you will measure it to be up. Okay. So let me tell you an experiment. Say you and your friend made two qubits and entangle them like this, right? And you stayed in Earth, and your friend went to Mars, all right? So you have two entangled bits, but you have separated them. The point about entanglement is that once you have entangled, you don't need any sort of physical connection, anything, to maintain an entanglement, all right? So that's what it means. Now, for example, you do a measurement on your qubit, or the quantum bit, and you measure an up. And then the other guy at the other end in Mars will readily measure it to find that his qubit is in down direction. And if you measure it to be down, your friend will measure it to be up.
How do you make sure the qubits are in the same position?
So there are physical techniques to make two entangled qubits. So once you have entangled, they are supposed to remain entangled irrespective of their physical distance. What I'm not telling you is how do you make entanglement. So, but that is one of the big part of quantum computing research. Right. So now, what you need to take from this is that, say you are given two entangled bits as a birthday gift, and then what you can do. And that's the thing, that first, irrespective of their differences, you can still measure that. Like if you measure one up, other one will be down. So there is a correlation between them, irrespective of how much distance there is between these two qubits. So that's what is called entanglement. Okay. Now let me try to give you a sense of why do we get quantum, why is it the case that quantum computing in certain cases can give you certain advantage. So one of the important things about quantum computing is that called quantum parallelism. What does it mean? So it's not all, quantum parallelism is not the only reason why quantum algorithms give you certain advantages, but this is one of the reasons. And you can think about it like this. We have already seen in the last slide, we have seen that you can create a superposition of states, meaning that one bit can be both up and down at the same time with certain probability. If you have two bits, then you have four different input combinations. Say you have two inputs for an f, like a function, and the input can be 0, 0, 0, 1, 1, 0, 1, 1, right? And so to calculate if the function for each of these combinations, you will need 4 trials, right? Think about a quantum computing case. In case of quantum computers, you can create an input state that is a linear superposition of all these 4 combinations. And now if you input this wave function to this function f, at the output you will get, what will you get? You will get a wave function for which each of this function has been calculated at the simultaneously. So it seemed like that in one shot you have calculated all of these 4 functions altogether, rather than having to go through it 4 times, right?
Why you are dividing by 2?
So that's because this is a wave function. Wave function. This is how the wave function is represented. The thing is, if it's to something called normalization, and it means that the coefficient in front of each of these wave vectors, like square of all these coefficients, needs to be equal to 1. So, but the sense is that what is inside the parenthesis. So again, the idea is that if we can create a superposition of state as the input, the function seems to have calculated all the output results at the same time, rather than having to go through many cases. So that's one reason as to why this thing. Okay, that's pretty cool. But the thing is that that's not all, because when you measure the output, you will measure only one output over here. So although internally it calculates all the input function, to still get the output, right output for each of these cases, you will need to do some more measurements. What the bottom line is that using this technique with something else called something else called interference, you can create all these source algorithm and other things. But the basic thing is superposition and entanglement. All right. So let me go back here again. So how did quantum computing advance over the years? First thing, in 2001, IBM demonstrated that it basically took 15 as an input and showed that it is a product of 3 and 5. So that's what it showed in 2001. So basically it factorized 15. It's a small number, but it was a pretty heroic deal back then. Then 2007, 2012, 2014, 2000, all of these things, many things happened. The largest number was something like this. Right? So let me try to give you a few ideas about how does the system looks like. Okay. So there are multiple techniques as to how you can make a quantum computer. The most popular ones are something called ion traps, and the other one is superconducting qubits. Okay. So most of the big companies are working with superconducting qubits. On the other hand, many others, some of the other ones are using ion traps. So how does the device look like? Now you have seen chips, right? If you open up your laptop or your phone, you will see a chip. Here also you have some sort of a chip, except for the fact that here you have individual ions in the chip. Individual ions meaning that, for example, do you know what this element is? Do you know what this element is?
Ytterbium?
Ytterbium. So this is an element called ytterbium. So what you are looking at here is that each of these dots that you see over here, I don't know whether you can see it, but each of these dots represent an ytterbium atom. So in this case, you have 72 ytterbium atoms. Alright. And each of these ytterbium atoms work as one quantum bit or qubit that can show, that shows superposition and entanglement. Alright. How does the physical, so basically in the chip you can have this kind of atom sitting there and all these things. This is how the setup looks like, and you probably cannot guess what is what. but over here there is a vacuum chamber somewhere, probably here. You see a vacuum chamber? Okay, so there is a vacuum chamber where the chip is, and in the chip you do all the calculations. So this technique is called ion traps, and ion trap is one of the techniques to do quantum computing, and is very popular. The other thing is superconducting circuits, and this is how the setup looks like. One of the things about superconducting qubits is that you need to operate these qubits at extremely low temperatures. For example, here you have 20 millikelvin. And what is room temperature? How many kelvins is room temperature, do you know? Around 300 Kelvin. So the quantum computer, the main chip remains at 200 millikelvin, and that's what is shown here. This is a dilution refrigerator, and at the end of this region, the chip remains there. And then you have multiple stages of computing system, different chips and other things, and altogether that's the quantum computer. But the main thing remains at very, very, very low temperature. Okay. So then the question is, why do we need such low temperatures? And what are the challenges of quantum computing? The thing is this. So, why do you have to do it at low temperature? And you can also see that we started talking about quantum computing in around 1990s, right? Why is it like now it has been 25 years, but still why don't we have quantum computers on our cell phones? Stuff like that. That's because there are some number of fundamental challenges. And the fundamental challenge is that the qubits are very hard to deal with. Okay. So think about the transistors in our chips. So say for example your cell phone chip, right? The iPhone chip, right? How many transistors are there in this chip? Guess, million, thousand. So order of magnitude, are there 10,000 transistors, 100,000, 1 million, 10 million, 100 million? How many? 10 million. Any other guess as to how many transistors are there?
I'd say 100 million.
100 million?
A billion.
1 billion? 10 billion? Okay. So actually in our cell phones there are 10 billion transistors. Yeah. So can you imagine how big a number 10 billion is? So for example, how many, what is the world population right now? 7 billion. So we have more transistors in our cell phones than the number of people, right? And each of the transistors are much well behaved. So the point is that there are so many transistors in our chips, and they are very, very well characterized, well behaved, meaning that ideally they don't die soon. Like they actually run pretty well. Like the amount of use we do, the transistors themselves are extremely reliable. Like it's something like it's probably more reliable than anything that you have seen in the entire world. So, and the other thing is also that why is information technology so big? Like why is it a revolution? The thing is that over the years, the amount of the cost has gone down exponentially. Today, we fabricate the number of transistors that we fabricate every day, like all the chip companies together, is more than the number of letters that are printed in all of the newspapers, all the books, all the world. Okay, so we make more transistors than all the letters every day. And what is even amazing is that each of the transistors costs making each of the transistors costs much less than printing a letter in your newspaper. So that's how cheap that technology has become. Although your cell phone costs you like $2,000 maybe, individual transistors are very cheap. Like that's how it happened. Back in 1950s, that was not the case. Transistor costs like maybe $1,000, $10,000. Now it is much less than anything that you buy in your. So that's how much the technology has evolved in the transistor technology. But that being said, qubits are neither reliable and not easy to make. So that's the thing. It's all nice when Shor's algorithm came up and showed that you can do these amazing things, but physically to have make a quantum bit is hard. It's very hard. And also, making one qubit is hard, but to do computation, you need more than one qubit. And having more qubits that are also well behaved in a system is even harder. So how many qubits do we actually need to do something useful? It's actually probably of the order of, like, even with 100 good qubits, you can do a lot more. With 53 very good qubits, you can actually do certain things much better than any supercomputers around. And Google actually 3 months back announced that they have demonstrated something called quantum supremacy. Quantum supremacy means that you can solve a problem in a quantum computer that any other computers in the world currently cannot do in a reasonable amount of time. But even for that, you need around 53 or 56 qubits at least. To solve the RSA cryptography problem, you need 4,000 logical qubits. It's nothing like a billion transistors, but still 4,000 is a large number given where we are right now, because now making one good qubit is already hard. Okay, so where does the hardness come from? The hardness comes from the fact that, think about a regular digital bit. Either it's 0 or 1. Okay. Now, it's 0 or 1. So, for example, how do we represent voltage? Say this is the voltage scale, and say this is 0 volt, and say this is 1 volt. 1 volt is the voltage at which our microprocessor operates these days. So, say even if the voltage, in the environment we have a lot of noise and other things, right? So even if the voltage is says between 0 to 0.2 volts, you can say that it's logic level 0, or maybe even higher, maybe 0.2. It's like 0, and also say up to like 0.6 to 1 volt, you will call it a logic level 1, right? So as simple as this. Even if you have noise and other things, you can just say represent the bits digitally. And also to go from 0, like if you have to have a very large noise to make a 0 to 1 and 1 to 0. So we're talking about noise. In quantum computing, what happens is that you need the exact analog value of the qubit to do the quantum computing. In quantum computing, a qubit is represented by something like this. Okay. So here you have two coefficients, alpha and beta are complex numbers. And by alpha, what it means is that if you measure this qubit, the probability that you will get 0 is alpha squared, and probability that you will measure a 1 is beta squared, and beta squared 1 minus alpha squared, like this. The important thing is that the analog values of alpha and beta are very important, and that's why it's hard, because it is affected by noise. So if you have a little bit of noise, then your system will go crazy. Your alpha beta values will go. So that's that. What is even more important is this. Okay. So So the next question is, why do we need to go to very low temperatures, at least for superconducting circuits? Because the amount of noise that you have in the system reduces significantly at low temperatures. First of all, superconductivity, you need like 1 Kelvin or 2 Kelvin, but then to have a very little amount of noise in the system, you really need to go to something of the order of 50 millikelvin or so. Okay. So the thing that we talked about is that the system is affected by very affected by noise. Okay. So one way of reducing the effect of noise is to have the qubits, keep the qubits very isolated from your environment. Okay. So you can make a very shy qubit that's just like a very shy person, stays in his office, works and then leaves, doesn't talk to anyone. And that kind of a person is not affected by the environment, so he will be, well, whatever state we put in there, he will be in that state for a long time. On the other hand, if you have a qubit that interacts with the environment a lot, then what will happen? You program some alpha, beta or analog values into the qubit, and over time it will just get randomized. It will, this alpha values, beta values, or the analog qubit values will change uncontrollably. Okay. So that's a kind of an example of a bad qubit. So a good, like ideally you would want a qubit in which that is less affected by noise, and to have it less affected by noise, you want to have the qubit isolated from the environment. Alright. But then the problem is that if someone is isolated, it's hard to interact with him. Right? If you have a shy person, he's very good at what he does, but it's very hard to interact with that person. So similar thing happens in a qubit as well. If a qubit can retain its information for a long time, it's very hard to program that qubit as well as get data out of it. Basically, programming and like reading the qubits is extremely slow. It happens so. All right. So that's the trade-off. If you want to have a low noise qubit, controlling it is very hard. If you have a qubit that is very easy to control, it is very noisy. So these are all these challenges that are there along in quantum computers. So for example, just to give you an example of how good the metrics are. For example, in superconducting qubits, they're pretty fast. In the order of 100 nanosecond. 100 nanosecond is not really fast when you consider the chip that you have in the iPhone, because there the transistors work at picoseconds. Do you know what picosecond is?
10 -12. 10 -12.
Yeah. 1 picosecond is 10⁻⁻12 second, and 1 nanosecond is 10⁻⁹ seconds. So you can clearly see that these guys are extremely slow compared to CMOS or the transistor technology. We'll get back to it. But these are like superheroes compared to the other technology, that is ion trap. So ion trap is of the order of microseconds. So a microsecond is 10⁻⁶ seconds. So these are actually much slower. But at the same time, the error rate of superconducting circuits is very bad. So we'll not talk about what it means, but it's very bad because it's fast, it's bad. On the other hand, if you think about the error rates or the error or the noise performance of ion trap qubits, it can hold the information of the order of seconds. On the other hand, in superconducting circuits, it can hold the quantum information probably not more than 10 nanosecond or microsecond or so. So that's kind of the thing, that there are trade-offs along with, in particular, with many of the attributes. All right. So last thing that I want to show is where are we? Like what is it that we want to do? So how many qubits do we need for quantum computing to be useful?